Hi everyone, welcome to our channel Physics, where we actually learn physics. So in today's lecture we are going to solve this problem that you can see on the screen. Okay, the problem is very simple. This is based on units and measurements. Over here we are going to find out the dimensional formula for these quantities. You can see there are four quantities that I have listed over here. Okay, so we are going to find out the dimensional formulas for all these quantities. So let's see what are these quantities. First one is the universal constant of gravity, that is capital G. You all must be familiar with this. Then there is surface tension, then there is thermal conductivity K, and the coefficient of viscosity eta. Okay, so let's solve one by one. So we'll go with the first one, that is the universal constant of gravitation. Okay, now the trick over here is, the first thing is you all have to know the formulas related to all these quantities. Without the formulas you cannot solve the dimensional formulas. So by hook or crook you must know the formulas behind each and every quantities. That is the only way, otherwise no, you cannot do it. Okay, so assuming that we all know the formulas, we are going to start with this. So the first one, as you can see, is the universal constant of gravitation, that is capital G. Okay, now what is the formula related to G? So you all must have heard about the Newton's law of gravitation, isn't it? The Newton's law of gravitation, isn't it? Now, according to the Newton's law of gravitation, two bodies having masses m1 and m2, okay, two bodies having masses m1 and m2, and the bodies are separated by some finite distance, let's say capital R. Okay, these two bodies attract each other with some force, okay, which is nothing but the gravitational force. So according to the Newton's theory, the force of gravitation between the two bodies having masses m1 and m2 separated by a distance r is given by a formula F is equal to G, the universal constant of gravitation G, m1 m2 divided by r squared. Right, this is the formula we all have already studied many times, isn't it? So this is the formula using which we are going to find out the universal constant of gravitation. Now there are actually many formulas associated with capital G, but all of those are actually derived somehow from this formula only. So what we are going to do is we are going to use this most basic formula, as you can see here. Okay, so what we will do is, first of all we will arrange this, okay, for capital G. Okay, so let's see what we get. Capital G will be equal to F R squared divided by M1 M2, right? That will be the formula for capital G. Now we have to find out dimensional formula for capital G, isn't it? So simply we can see here that the dimensional formula for capital G, okay, universal constant of gravity, will be nothing but the dimensional formula for F, then dimensional formula for R squared, and then over here we have M1 and M2. So dimensional formula for M1 and M2. Now over here, if you look at this equation carefully, here there is R. R is the distance which is associated with length, isn't it? Then M1, M2, these are nothing but masses. Now length and mass, these are nothing but the base quantities, isn't it? The base quantities, okay, which are already defined in SI unit system. Now if you know the trick, whenever we find out the dimensional formula for any physical quantity, first of all we represent that quantity in terms of the base quantities. So over here R, M1, M2, these are already the base quantities. Now the only quantity that is remaining is F, the force. So first of all we will have to find out the dimensions for F, because the dimensions for R squared are simply known, right? r squared, so it will be just L2 because it is associated with length and there is power 2. So we can say r squared has got dimensions 2 in length, right? 2 in length. Then similarly m1 has dimensions m1, isn't it? Because it's just mass, it's a base quantity. M2, it has got dimensions m1 again, isn't it? So it's all simple. Only thing that is remaining is capital F, right? That is the force. So let's find out what is the dimension of force, and then we are through with this problem. It's very simple. So what is force? Force is nothing but mass into acceleration. This is the formula that we have been learning since our 7th or 8th standard, right? Okay, now let's try to represent force in terms of the base quantities. So force is equal to mass is a base quantity, acceleration is a derived quantity. So first of all, we have to represent acceleration in terms of the base quantities. Now what is acceleration? Nothing but rate of change of velocity, isn't it? So it is written as dv by dt. dv by dt is a differential form actually. Okay, we write acceleration like this in differential form. dv is a small change in velocity and dt is the small time. Okay, but again velocity is not a base quantity, isn't it? So we have to again write this velocity in terms of the base quantity, right? Now what is velocity? Velocity is nothing but rate of change of displacement, isn't it? So we can write here m d by dt. Now what is velocity? Dx by dt, rate of change of displacement, isn't it? Now we can just find this out. F is equal to m. Now if we multiply this, okay, now this will become double differentiation, okay, d2x upon dt squared. Now that becomes the formula for force, okay, mass into acceleration. Now can be written like this. This is acceleration, isn't it? Okay, now here if you see, we have actually represented force in terms of the base quantities, isn't it? Mass is a base quantity, then x is a displacement is some length, isn't it? So it's a base quantity again. What is there? This is time, isn't it? So time is also a base quantity, right? In this way we have represented f in terms of base quantities. Now we can easily find out the dimensions for force. So the dimensions for force will be nothing but m1, right? Now x here, look at this x. So it is L1, then there is t squared, but its denominator, that's why it will be t raised to minus 2. So we can say force has dimensions 1 in mass, 1 in length and minus 2 in time, right? So this is the dimensions for force, okay, m1 L1 t raised to minus 2, isn't it? Now we have everything that we need. Okay, look at this. This is the quantity that we are finding out the dimensional formula for, right? Now we know the dimensions of f, r squared and m1 and m2. Let's put all these things, okay, in our formula and let's see what we get. So the dimensional formula for g will be equal to, first of all we have force. What is the dimensional formula for force? m1 L1 t minus 2, isn't it? Then there is r squared, so it will be L2, right? Then we have m1 and m2, right? So it is again m1 for m1, then m1 again for m2, isn't it? Now let's see what are the things that will cancel up. Okay, so first of all g is equal to this m1 will cancel up. Okay, what you can do is you can take this to the numerator and you will find out that anyways it cancels up, the powers become 0. Okay, now look at this. There is L1 here, there is L2 here. So if we do this, this will be L3 and this is t minus 2, and still we have 1m1 in the denominator, right? So it will be m1 here. Now let's arrange this again. Finally what we get is G is equal to M minus 1 L 3 T minus 2, right? T minus 2. And in this way we have actually found out the dimensional formula for capital G, right? What is the dimension of G? Here it is. G has dimensions -1 in mass, 3 in length, then -2 in time. That's it. We have actually got the value that we are looking for, isn't it? Now let's move to the next one. The next quantity that we can see here is the surface tension S, isn't it? So let's find out what will be the dimensional formula for surface tension, isn't it? Now, what is the formula for surface tension? So surface tension is equal to force per unit length, right? If you have not yet studied this, you are definitely going to study this in the coming chapters. Surface tension, this is a property related to liquids. Okay, you will definitely learn this, but for now I'm just going to tell you the formula: force per unit length. Okay, now the dimensional formula for S will be nothing but the dimensions of F divided by the dimensions of L, right? Now we have just found out the dimensional formula for force, okay, in the previous problem, that is M1 L1 T minus 2, isn't it? Divided by, now this is length, this is a base quantity, so we can directly write L1, okay? Now you can see L1 will cancel, right, because it is in the denominator as well as in the numerator. So what will prevail here is M1 T minus 2, right? So in this way we can see that surface tension S has dimensions 1 in mass and -2 in time, isn't it? Surface tension has dimensions 1 in mass and -2 in time. This is how generally we read it. Okay, so in this way we have found out the formula for surface tension. Now let's move to the next one. The next one is the thermal conductivity K, isn't it? The thermal conductivity K. So let's do this. First of all, we must know the formula for thermal conductivity. Okay, so before I tell you the formula, first of all we have to just understand few things. So I'm going to just tell you a little bit about thermal conductivity. Okay, let's go. Okay, now let's say we have some piece of a substance. Okay, it may be any material, doesn't matter, but let's say that the piece has a length x, for example. Okay, it has a length x, and let's say the cross-sectional area over here is capital A. And not only this, let's say the temperature at one end of the piece is T1, whereas at the other end it is, let's say, T2. Okay, so that you can see the temperature difference is T1 minus T2. Okay, let's say that T1 is greater than T2. Okay, that means now you can see there is a temperature difference between the two ends of the same piece. Okay, now because of this temperature difference, definitely the heat will flow from the hot end to the cold end. That means heat will flow in this direction. Now how much heat flows per unit time? How much heat flows per unit time? Over here Q is the heat, T is the time. The amount of heat that flows per unit time depends on few parameters. First thing, it will definitely depend on the temperature difference, isn't it? More the temperature difference, more will be the heat flowing per unit time, isn't it? Imagine that one end is very hot, another one is not so hot, so definitely heat will flow very fast, isn't it? At the same time, it will also depend on the area of cross section. More the area, more the heat that flows, right? And it will also depend inversely on the length of the piece or the distance between the two ends. isn't it? More the length, more time it will take for the heat to flow from one end to other, isn't it? So the amount of heat that flows per unit time depends on three things. One is area of cross section, secondly the temperature difference, and the third is the distance between the two ends, isn't it? Okay, but there is one more thing that it will depend on, and that is a characteristic property of the substance, isn't it? It will also depend on the substance, isn't it? Imagine that you have a piece of a copper or a iron, for example, and you have a piece of a wood. Okay, so if you have these two different substances, definitely the amount of heat flowing per unit time, okay, will be more in copper or iron, okay, as compared to the amount of heat flowing per unit time in case of the wood, isn't it? So over here, that's why we have to include one more term here, that is a characteristic property of the substance, and that is nothing but the K. It is called as the thermal conductivity of the given substance, okay, of the given substance. Okay, so K is a very basic characteristic property of any substance which actually tells us how much heat will flow per unit time, okay, depending on the area of cross section, the length and the temperature differences. But this is a very basic characteristic property, okay, which actually describes the flow of heat. Okay, no problem. A, delta T and X as it is. So K is a constant associated with every substance. Now we have to find out the dimensional formula for K, isn't it? So let's arrange our equation in terms of K. Okay, so K will be equal to, let's see what we get. So it will be Q X, as I can see, divided by A into small t, the time, okay, then we have delta T, the temperature difference, isn't it? Okay, you can check this arrangement, just pause the video and check it. Okay, now this is the formula for K. Now we can find out the dimensional formula. So the dimensional formula for K will be equal to dimensions of Q, the heat, dimensions of X, the length, then dimensions of area, and the dimensions of the time, and the dimensions of the temperature, isn't it? Now, as we know, while finding out the dimensional formulas, we first represent every quantity in terms of the base quantities, isn't it? So here also we have to do the same thing. Okay, like for example, Q is heat. Heat is not the base quantity, isn't it? It is a derived quantity. That means it depends on many other base quantities. So first of all, we have to represent it, or we have to find out the dimensions of Q separately by representing it in terms of the base quantities. Secondly, if you look at all other quantities over here, like this X, this is nothing but length. Length is a base quantity, so no problem with this. Then time. Time is also a base quantity, no problem with that. Again, look at this. Thermodynamic temperature. It is also a base quantity, no problem. What remains is this area. Area is not a base quantity. Area is what? Length into breadth, isn't it? Breadth is also some kind of a length, isn't it? Length is a length. So that means we can find out the dimensional formula for area easily. Okay. Now what is important here is this Q. Now we have to find out the dimensions of Q first, then only we can do it. Okay. So let's first find out the dimensions of Q. Before that, I will just write here the dimensions of X. So dimensions of X is nothing but L1, because it's just the length, right? Then dimensions of time, that is nothing but T1, isn't it? And dimensions of the temperature, what it will be? Nothing but K1. K is Kelvin, unit of temperature, right? So in this way we know these things. Now what is area? Look at this area. Area is length into breadth. So dimensional formula for area will be equal to L2, right? Because both of these are associated with some length. Length is a base quantity. Okay, so in this way we have found out all these things. Only Q is remaining. Let's find out the dimensions of Q. Q is a energy, right? Q is a form of energy. It's a heat. Heat is a form of energy. So we can use any formula for energy and it will give us the same dimensions. So what I'm going to do is I'm going to use the simplest formula for energy. Okay, that is nothing but 1/2 mv squared. This is the what? This is nothing but the kinetic energy, isn't it? This is the kinetic energy. So we can do this easily. Okay, this is 1/2 mv. What is v? V is nothing but distance upon time. It is squared, isn't it? So it is 1/2 m x squared upon t squared. So in this way we have represented this energy in terms of base quantities, because all these are base quantities. Okay, now the dimensions of energy, okay, can be said to be the dimensions of heat also, because both are the forms of energy. Now let's find out. So 1/2 is a constant, so it will have no dimensions, but this mass, it has dimensions 1 in mass. This is x squared, that means it has dimensions 2 in length, and here time squared, that means t raised to -2, because it is in the denominator, right? So in this way we have found out the dimensional formula for Q also. Now let's go here into the main formula of K. Okay, K is equal to Qx upon AT delta T. Now let's put all the values. Let's put all the values. As I said, K is equal to Q x divided by A T delta T, right? Now K is equal to, what is Q? What is the dimensions of Q? We have just found out M1 L2 T minus 2. Then X, it's a length, so L1, we have just written all these things above. Okay, area, it's going to be L2, right? Then this is time, so it is T1. Then this is temperature, so Kelvin 1. Okay, now let's solve this, right? Let's just simplify this equation. Let's see what are the things that cancel up. So I guess this L2 also cancels, right? Other than that, I don't think anything else cancels. Okay, so the dimensions of K is going to be, first of all, we have M1, then we have L1 also, you can see here, then we have this T raised to -2, and this is T1. So if this T1 goes to the numerator, then it will be T minus 1, and therefore T minus 2 and T minus 1, that will be T minus 3, right? And again there is K1 also, so that will be K minus 1, isn't it? So in this way we have found out the dimensional formula for thermal conductivity, isn't it? So as we can see, the dimensions of K are in front of us. It has dimensions 1 in mass, 1 in length, -3 in time, and -1 in temperature, isn't it? So in this way we have got our answer. Now let's move to the last quantity that is asked in the question. Okay, so the last quantity is the coefficient of viscosity. Okay, so first of all, let's write down the formula for coefficient of viscosity. Okay, now the coefficient of viscosity is associated with the friction in liquids. Okay, the friction in liquids. Okay, the layers of the liquid, okay, when the liquid is flowing, then the adjacent layers of the liquid, okay, oppose each other's motion by exerting some kind of a force, and that force is called as the force of viscosity, isn't it? So The formula for force of viscosity is given as minus eta, okay, minus eta A delta V, I mean dV upon dx. Okay, this is the formula. Now eta is the coefficient of viscosity, A is the area of the layers in contact, then dV is the change in velocity, and this dx is some distance. Okay, so you will learn about all these things in the subsequent chapters when you will actually learn the viscosity. Okay, but right now I can just tell you the formula. Okay, now we have to find out the dimensions of eta, right? So let's arrange this equation first of all. So from this equation I can write eta is equal to F, okay, F divided by A into dV by dx, right? This will be the formula for eta. Now let's find out the dimensions of this. First of all, let's arrange this equation. Okay, so I guess this will be F upon A dV. Let's just simplify. Okay, I will just write this dx up, right, because it will go here. Now the dimensions of eta will be nothing but the dimensions of force, the dimensions of dx divided by the dimensions of area and dimensions of velocity. Okay, it's a small change in velocity, but it doesn't matter whether it's a change in velocity or velocity, it will have the same dimensions only. And this dx is some length, so it is a base quantity. Okay, now let's first write down the dimensions of each and every quantity. Now the dimensions of force. What are the dimensions of force? We have just found out. This is nothing but m1 l1 t minus 2. If you see the first example, the first quantity that we solved, over there itself we had found out the dimensions for force. Then dx, it is just a length, so we can just write L1, right, because length is a base quantity. Then there is area, right? Area we have just seen in our previous example. Area is length into breadth, right? It has got units meter squared. That means it will have dimensions L2. Okay, then dV, right? What is velocity? Nothing but some displacement upon time. So therefore we can say the dimensions of velocity or change in velocity will be nothing but L1 for this length, okay, x, and t minus 1 for this time here, isn't it? So in this way we have got everything that we need. Now let's put all these quantities in our main equation. So dimensions of eta will be equal to, first of all, force. So force is 1 m1 l1 t minus 2. Then dx, it is going to be l1. Then we have area, that is l2. Then we have this velocity. So velocity has dimensions 1 in length and minus 1 in time. Okay, no problem. Now let's solve this. Okay, as we can see here, there is L2 here. Okay, this will cancel with L1 and L1, isn't it? Okay, that will cancel up. Now what else cancels? I guess this one, t minus 1 and t minus 1 from here. So that will be t minus 1 only, isn't it? Now let's write down everything that is remaining. So eta has dimensions, as you can see, 1 in mass. Then you can see there is length also prevailing, so that will be L minus 1, isn't it? Then we have this time term, so it will be t minus 1, isn't it? Is there anything else left? No, I don't think anything is left. Now you can see that the coefficient of viscosity eta has got dimensions 1 in mass, then minus 1 in length and minus 1 in time. That's it. This is our final answer. Okay, so in this way we have just found out the dimensional formulas for 4 physical quantities, right? The 4 physical quantities. One of them is the universal constant of gravity G, then we found out for surface tension, then we found out for thermal conductivity K, and the last one was coefficient of viscosity eta. So in this way, this numerical has been solved. I hope everything is clear, but still if you have any doubts, you can just ask me in the comment section. I will definitely try to answer as soon as possible. So thank you so much for watching this video, and I hope to see you in our next video. Thank you so much. Bye bye. See you.